Hello guys, uh, let's start 3D transformations. This comes in module 3. 3D transformations, as you know, if you ask me why transformations, because an original object when it gets moved or when it gets rotated, instead of showing, instead of calculating again, instead of redrawing it again, you can just tilt your camera to see the object. So transformations, as you know, there are 5 types: rotation, scaling, translation, sharing, and reflection. So the main topic of today is 3D rotation. Uh, Before that, let's just recap. In 3D, 3D point can be, of course, recognized with XYZ coordinates, and to make the machine understand, and for our transformations purpose, we do add a homogeneous coordinate. And you remember in 2D transformations, adding homogeneous coordinate, we got 3 by 3 matrix. Similarly, for a 3D point, if we add a homogeneous point, we will get 4 cross 4 matrix. And just to recap, if you ask me why homogeneous coordinate, the answer is to eliminate additions, and of course for combining various transformations. So let's see how exactly we can eliminate additions by using homogeneous coordinates. You remember 2D transformations, we had translation, uh, this is the equation 1001 xy. I will just, xy plus dxdy. I will just multiply xy, there is a point with 1001, it doesn't make any difference. Rotation, we had cos theta minus sine theta, sine and cos into the point xy. We will just add plus 00. Scaling, we had scaling factors into the point. Let us add plus 00. So if you see these 3 equations, combining above equations, we can say in general that the transformed point, or I can say the new point, is equal to matrix 1 into the point plus these matrix 2. So you can see here we have multiplication here as well as addition. Is there any way to eliminate additions? Well, the answer is yes. It is homogeneous form. So you can see here the 2 cross t becomes 3 cross 3. Each Cartesian coordinate with homogeneous will now become xh, yh, h. So where x is equal to xh by h, therefore xh will now become cross multiply h into x, h into y, h. If we set h is equal to 1, it becomes x y 1. Now the translation, scaling and rotation, which was looking something like this, will now get converted to 3 cross 3 using homogeneous like this. You can see there is only multiplication, no need. We have just eliminated addition. To support this point, in the class we saw about this example. In 2D translation, let us say there's a point at 2, 2, we have to translate till 8, 6 by adding 6 and 4. There's a point, it has to go all the way to 8, 6. How exactly is we add 6 units xy's and 4 units y's. So this is the original formula, right? So the new point is the old point plus the translation x. Now we have this addition, so let's see how exactly we can eliminate via homogeneous coordinates. So the new formula we have only multiplication. Apply the new formula, you will get 8, 6. The 1 indicates that it is homogeneous. So still we got 8, 6, whatever we got here by addition, with this multiplication, we got 8, 6. So essentially, homogeneous coordinates eliminates addition, point 1. Number 2, it is very helpful if you want to combine the various transformations. For example, the point goes to some other location, that is translation, and then if you want to rotate, then you scale it, then again inverse translation, inverse rotation, all these combining various transformations, you can do it with the help of homogeneous coordinates. So all these we have seen. I'm just recapping a bit. Now, yeah, as I said, we don't lose anything. It is easier to compose, and everything is just matrix multiplication. For coordinate system, for our purpose, right hand, left hand rule, it just goes like this. So just to determine which axis is what. Homogeneous, of course, it becomes 4 cross 4 matrix. Now let's look into 3D translation. There's a point x, y, z, which has to be translated to this location, x dash, y dash, z dash. So in 2D we had x and y, and in tx and ty, just add the tz parameter and the z dash parameter. So the z parameter. So z dash in the sense the new, I mean x dash, y dash, z dash means the new coordinates, the translated coordinates. So in the, I mean this is the formula, translation matrix into the old one. So T into K. As I said, in 3D transformations, translation, scaling, sharing, they're all pretty much straightforward. Rotation is where we find it a bit difficult. So just move on. So here is an object. We need to translate it. How exactly this gets translated? Well, the formula is this. We'll quickly move on. There comes inverse translation. For example, the object is here and it has gone to here, and again it has to come back negatively. So you just subtract it, and this is how the inverse translation looks. Now comes the major point, the topic of today's discussion, called 3D rotation. Now understand, 3D rotation, you can rotate any object in space in three types. One, of course, you should specify me the rotation axis, x or y or z or any arbitrary axis, and an angle, how much degrees you want to rotate. And of course, there's one more, whether you want to rotate clockwise or anti-clockwise. Now, the main point of discussion is 3D rotations are of three types. One is you can rotate any object via the coordinate axis, that is x and y, x, y, or z. Next is you can rotate any object via an arbitrary axis, that is your own axis. And if that axis is parallel to the coordinate axis, x, y, z, that becomes the second type. Third type is your own axis, called as arbitrary axis, not parallel to the coordinate axis. That becomes the third type. This third type is a bit tricky. Alright. So first one we'll see. First one, coordinate axis rotations. It is pretty much straightforward. Just a copy paste of your 2D rotation by just, and all you need to do is add the z coordinate. So let's see the z-axis rotation. So an object which will be rotated along the z-axis. So we know this formula from our 2D translation, 2D rotation. So if you rotate an object via z-axis, understand the z parameter will remain as such because you are rotating via z-axis. So since you rotate via z-axis, x and y, the other two will now be, the action takes place via the other two. So this is the formula. So P dash, the rotated point is now is equal to this matrix into the P, that is the XY. Alright. Now if you want to rotate the same object via x-axis, so what we shall do is, see, look at this line x, y, z, x. So x comes after z. So essentially in the z axis rotation, what you do is take this z axis equation, and wherever you have z, you replace with x, and wherever you have x, you replace with y, wherever you have y, you replace with z. That is, it's a cyclic rotation. So take this z-axis equation, and if you want to rotate with x, since x comes after z, so just replace the z-axis rotation. Wherever you have x, you replace with y. And wherever you have y, you replace with z. So x replaced to be y, and y need to replace with z, z need to replace with x in z-axis situation. So this is the formula. And if you want to rotate the object with respect to y-axis. So take the x-axis formula. Why? Because y comes after x. So take x-axis formula and replace, if you take x-axis, this is the formula, and replace y with z, z with x, and you will get y-axis rotation. So this is the y-axis rotation matrix. Now this is one type. Second type is arbitrary axis, that is your own axis parallel to the coordinate axis called xyz. Means to say, let us say here you are, and your this blue color line is your axis. It is your viewing angle. Now that axis is parallel to z axis here. In this diagram, your viewing, that is your axis, is parallel to the x axis. And in this diagram, your axis is parallel to the y axis. So that is what I mean by arbitrary axis, that is your axis parallel to coordinate axis. Now in this case, what exactly you need to do? For example, let us take x axis. So let us say there is an object. So what you should do essentially, there are three steps. One is bring that axis. For example, if you want to rotate via x axis, bring your arbitrary axis, bring your blue line to merge with your x axis, rotate it, and go back to wherever you are. So, this is how it looks like. Rotation about an arbitrary axis parallel to coordinate. The triangle is your object, and this blue line is your arbitrary axis. As you can see here, the blue line is parallel to x-axis. So all you need to do is come from the reverse for all the points. First is you should translate it. First, translate this blue axis, that is your arbitrary axis, onto the x-axis, because here we are taking as x-axis. You can see here, yeah, rotation axis, P. Merge to the x-axis, rotate it via x, and push back to wherever it was. So this red dotted, this is the question. This is A. The three steps. First step is bring this dotted line, that is your arbitrary axis, because we need to rotate via x-axis here. Bring that red dotted line, that is your arbitrary axis, towards the x-axis. Then rotate it, and then push back to wherever it was. So T, rotate, and inverse. So this completes this rotation axis parallel with coordinate axis. For example, I have taken as x-axis. You can take it. You can just go ahead with y-axis and z-axis as well. Now the interesting point comes. What if your axis is not parallel to any of the coordinate axes? Here, what happened? This red dot line, for example, this blue line. Yeah, for example, these lines are parallel with these z-axis, x-axis, y-axis. So this is the equation. The third type is, what if that axis of yours, that is called arbitrary axis, which is not at all parallel to any of the coordinate axes? This is a big deal. Now let us take this blue color line here. You can see here this axis is neither parallel to x, y, or z. In that case, how do you rotate any object with respect to that particular axis, which is not at all parallel to any of the coordinate axes? Well, there are 5 steps, 7 series of mathematics. We will see step by step. First step, the diagram, the original diagram will be the original equation, or the original scenario will be something like this. First step is bring this arbitrary axis, which is not parallel, to your axis. For example, that your axis can be, I mean, you should rotate this arbitrary axis via z or x or y. But the point is, first step rather is bring this arbitrary axis to origin. That is, it translates that the rotation axis passes through the origin. Second, rotate that arbitrary axis such that it coincides with your coordinate axis. It can be z, it can be x, it can be y. For 3D, always we will go ahead with z-axis because z-axis talks about depth. I'll repeat, this is the original scenario. First step is bring this arbitrary axis to origin, something like this. Second step, rotate this arbitrary axis such that it coincides with any of the axes. For example, z-axis. Third step, this second step itself has two sub-steps. There is 2a and 2b, which I'll talk about in a bit. Third step is rotate this object with respect to z-axis. And see here, the object was something like this. Now if you rotate via z-axis, we already know the formula, coordinate axis. So rotate it, it will come like this. Fourth point, inverse rotation. So we had the axis something like this. Now you inverse it to the origin. Fifth point, go back to wherever it was, inverse translation. So there are 5 steps. The arbitrary axis origin, rotate it via coordinate, rotate it such that it coincides with the coordinate axis. Third is rotate about that axis. Fourth one, inverse rotation, go back to the origin. Fifth one, inverse translation, go back to wherever it was. Now, to understand this in a very better way, we have, we have a video prepared by Hamreen. So he or she has prepared some 20 seconds video, which I'll play. You will understand in a much better. So as we saw, you can see here. So let us take the arbitrary axis, and there is a teapot. First step is coincide with the origin. Second step is rotate it such that it coincides with any of the arbitrary axis called z-axis. Next is rotate via z-axis. Next step is go back to the origin, and the last step is go back to wherever you. Let us look again. Let's say this is the arbitrary axis and the teapot is your object that needs to be rotated, and P1, P2 are this is actually a vector. P1, P2 are the points. Now we'll play again. First step, the arbitrary axis in space, which is not at all parallel to any of the coordinate axes, bring it to origin. First step. Second step, rotate it such that it coincides with z or x or y. Third step, if you have coincided with z-axis, rotate it via z-axis. Fourth step, go back to the origin, inverse rotation. Fifth step, inverse translation. Go back to wherever you are. So this video helps us in understanding the whole subject in a better way. The whole, the topic of discussion is 3D rotation about an arbitrary axis, which is not on the parallel to any of the coordinate axis. So I believe this video, this small 20 seconds video, helped us in understanding the point. Now let us dive deeper. So we now understood we need to combine all the x-axis, y-axis, z-axis matrices so that we get the final equation. So let's dive deeper. Let us take the example, one more example. This is the initial scenario. I have an object. You can consider this as a teapot. So P1, P2 is your vector. Step 1, bring that to origin. Step 2, rotate it such that it coincides with the z-axis. Why? Because we are assuming that the rotation axis projected to the z-axis. So step 1, bring to origin. Step 2, rotate it onto the z-axis. That is, rotate the arbitrary axis onto the z-axis. Step 3, rotate the object onto the z-axis. Step 4, inverse rotation. That is, go back. That is, rotate your arbitrary axis to the origin. Inverse rotation. Next, fifth step is inverse translation. Go back to where we were. Now, if you look at the mathematics, come from the right hand side. First step is translation. Second step is uh, you need to rotate this blue color arbitrary axis onto the z axis. Means you need to rotate via x-axis, you need to rotate via y-axis. So rotation of x-axis via some angle called alpha, rotation of this rotated around x-axis, you need to rotate that with y-axis with some angle called beta, and then you need to rotate that object onto about the z-axis with some theta. That is your original rotation. Next is these two are inverse rotations. So you rotate around the same y-axis with some angle called beta. You rotate some x-axis with some angle called alpha, and then inverse translation. So basically, these you should do to nullify the effect. Now we have seen this. We have seen this via the other example, via a video, via this example. Now let us look at how exactly we can do all this. Now this implies, as we have already told, 5 steps: origin translation, rotation, rotation of the axis, rotation of the specified object. Next is inverse rotation, inverse translation. Step by step we will now see. First step, translate the object such that the rotation axis passes through the origin. Now to understand this, let us see the initial position. This is the blue color line is the arbitrary axis with Q1, P2. Q1, P2 is actually a vector, and this is the object. Now let us consider this vector as a unit vector. This solid line is your unit vector, and P1 has x1, y1, z1. P2 has x2, y2, z2 coordinates. Let's name it. And all we should do is bring the whole u guy to origin. Before that, we have earmarked P1 and P2. Now this u is a unit vector, and let us name unit vectors coordinates as ABC, where A, because this is a unit vector, we know the vector's definition is equal to the vector divided by the magnitude of the vector. So what is ABC? You can see here the components of the rotation axis vector is ABC, where ABC is the vector divided by the magnitude of the vector. What is A? It is x2 minus x1 divided by the magnitude of this. V is equal to P2 by P2 minus P1. So x2 minus x1, y2 minus y1, z2 minus z1. The magnitude is, remember, square root of this. Square root of this. So, since we have named as ABC, where A is x2 minus x1 divided by the magnitude of this vector, B is y2 minus y1 by the magnitude, C is z2 minus z1 by the magnitude. So ultimately this, when you apply this formula, this unit vector, that is this arbitrary axis, will now coincide with origin, so that it now looks like this. Yeah, you can see here. Yeah, this is the original equation, and this is the final. And what we need to translate is the P1. So P1, P2, we have something like this. P1 is x1, y1, z1. If you can pull that x1, y1, z1 inverse, that is minus x1, minus y1, minus z1, your axis will now coincide to the origin. To explain you in a simple way, please understand. Let us say P1 is 10, 20, let's say 5. And P2 is, let's say 15, 25, Now, how do you pull this P1 to origin? P1, mind you, it is 10, 20, 5. So if you can subtract minus 10, minus 20, minus 5, that is 0, 0, 0. That is how P1 comes to origin. So minus 10, minus 15, minus 5 if you subtract, and your P1 will now come to origin. That is what I mean by getting this guy to the origin. So this is the translation matrix P. What are we doing here is, remember we had this equation and we are coming from the right hand side. That is, what is this T? This T is this matrix. All right. Now that is step 1. That is, in the final equation we are done with T. Now we will go to step 2. That is, rotate the object so that the axis rotation, that is your arbitrary axis, coincides with one of the coordinate axes. Now here, the one of the coordinate axis we have considered as z-axis. So what you need to do is, we will go back to the previous step. This is the final step now, final output of your first step. So P1 was here, you can see here, P1 was here, now P1 is here, P1, P2, the arbitrary axis, and the arrow mark is in XY plane, that is, arrow mark is in this first quadrant. So all you need to do is bring this P1, P2, let P1 be here itself, bring this P2, rotate this P2 such that it will now coincide with z-axis. But as we already know, if you rotate any arbitrary axis via any axis, that particular axis will remain same, but it will reflect other two. It will have an effect on other two. Now coming to this scenario, current scenario, P1, P2, that is the arbitrary axis, if you want to rotate this axis and merge it and coincide with z-axis, z-axis remains same, but x and y rotation happens. Now that is the meaning I said it has 2 steps. So I have earmarked as 2a and 2b. Now let us understand this. We will formulate the transformations so that the rotation axis comes to that axis. We can use the coordinate axis rotations to accomplish this alignment in 2 steps, as I told. First step is, we will rotate about the x-axis such that, and then we'll rotate around y-axis. First step, the x-axis rotation gets this vector u, that is already we have in the first step we have coincided with the origin. The x-axis rotation gets this vector u into the xz plane. Next step is, since we have this xz plane, now we will rotate this u dash, that is the output of 2a, anti-clockwise such that it will now coincide with z-axis. I'll repeat, all we want is the P1, P2, however it is looking like this, arrow mark. P1 should stay here, P2 should come onto the z-axis. The z-axis means x-axis rotation should happen and y-axis rotation should happen. Now, there are 2 steps. Step number 2, bring that unit vector to xz plane by rotating that via x-axis. So the output is something like this. Second step, bring this u dash, that is this the output of 2a, rotate it such that it now comes to z-axis. You can ask me one question: why can't you do it in one shot? Well, in 3D, if you want to coincide with one axis, the other two axis definitely comes into picture. So you need to rotate with keeping other two axes in mind as well. You can see this statement. Unit vector u is rotated above the x-axis to bring it to the xz plane. Second step, and then it is rotated. It means this u. This u is rotated around y-axis such that it aligns, it coincides, it merges with z axis. Now this is a theory. I have written this theory. Now how do you put it into practice? Step 2a, that is this 2a's theory is what? Rotate the u means the output of the step 1, that is the unit vector coinciding at the origin. So rotate that with x-axis such that it now comes to xz plane. Don't confuse, this is yz. This u dash is just the shadow of u, I'll tell you. Such that x-axis, rotate this u around the x-axis such that u comes to xz. This is accomplished by rotating u dash. What is u dash? The projection of u in the yz plane through an angle alpha onto the z-axis. Now, to make you understand this, look here. We have this original line, that is the output of u, output of step 1. We coincided that with origin. So u has ABC, where a is the fraction cosine x2 minus x1 by the magnitude of ABC. B is y2 minus y1 by magnitude. C is z2 minus z1 by the magnitude. We had this here. Now what we need to do is, this u should now come to xz plane. Now it will not come as such. So the viewer will be viewing this u something like this from here, this angle, let us say. So this becomes the actual point. Now whenever you view this u vector from this angle, you will see the projection of u somewhere here. Let us call that as u dash. U's original coordinates is ABC. When you project this u via x-axis. That is, now understand your axis. That is, your view is parallel to now x-axis. So since your view is parallel to x-axis, that means you are rotating around you're rotating around x-axis, so that your x-axis becomes 0. That means you're not changing via x-axis. 0 means you're not playing with x-axis because your view is parallel to the x-axis. So BC remains same. I'll repeat. You need to rotate this U around the x-axis such that this U comes to xz plane. Now, how exactly it comes is, let us say the user is viewing this U such that his view is parallel to x-axis. So since his view is parallel to x-axis, the x-axis, that means whenever you rotate it, the x-axis remains unaffected. The other guys changes. So other guys BC, now BC comes here. Now these are all called as normalized projections. You can see here I'm drawing it, and again a dotted point here. Use it. These are all normal view only. But since we want the direction cosines, that is trigonometry, that is the cosine and sine angles. As you know, cosine and sine always depends on orthogonality of the equation, or orthogonal values. So this is not 90 degree. So what you do is draw a perpendicular so that it coincides. It has an angle of 90 degree. Now this angle is alpha. Now you can apply the rotation direction cosines. So now to understand in basic common sense, so use something like this. U's projection is U dash. Now if you go here, if you if you see from the top, U dash projection will now come to U sub. But since you want to rotate it, trigonometry comes now into picture. Trigonometry always stands for 90 degrees. So you need to draw a normal. You need to draw a perpendicular. So 90 degrees. Now you can have this alpha. Now what is this alpha? Now let us understand in basic common sense. Now let us say this is 50 degrees. Now what you need to do is you should keep on rotating this u dash 50 degrees. How long? Such that this u dash will now come to xz plane. That is what do you mean by alpha? Now to get the direction cosine prints the rotation parameters. In the rotation matrices you saw that cos theta minus sin theta cos theta. So to get those, so draw a normal, you get, and then you compute. So you take this triangle now, this u dash, the origin, and this part, where you drew the normal. Now this, if this is the alpha, this is 90 degrees. So the opposite is b. This is b now because this is 0, b, c. Why it is 0? Because your view is parallel to x-axis and you are rotating y x-axis. So x-axis A becomes unaffected. So this is your B and this is your C. So cos alpha is adjacent by hypotenuse. Adjacent is C. This is your hypotenuse. So if this is B and this is C, according to Pythagoras theorem, this is square root of these two sides, b square plus c square. Now let me call that square root of b square plus c square as simply d. So cos alpha is now adjacent c by d. Similarly, sin alpha is opposite by hypotenuse. Opposite is b, hypotenuse is d. That is root of b square plus c square. Now comes the equations. So we got this cos alpha and sin alpha as c by d and b by d. Now we should substitute these cos and sin values in the x-axis rotation matrix. Why x-axis rotation matrix? Because step 2a, that is your rotating this axis via x-axis. That is the reason your view is parallel to the x-axis. That is the reason this is 0. Next step is we will do around y-axis. Okay, since 2a talks about x-axis, we will substitute these cos alpha and sin alpha and in the x-axis rotation matrix. Why? Because 2a talks about x-axis. For your sake, I have given you the x-axis rotation matrix equation, rotation matrix. So wherever cos theta we have, we will substitute c by d. Wherever sin theta we have, we will substitute b by d. So this is how your Rx of alpha gets the final equation, something like this. Now you can ask me, what is this Rx of alpha? Now you can see this here. We're done with T in the first step. Now Rx of alpha is being calculated like this. Now what is left out? Ry of beta. Now 2a's result is Rx of alpha is something like this. Now what is the result? So the original vector was something like this. This is the output of step 1. And step 2, what we did in 2a, the direction, we saw u via this x-axis. So we got u dash, that is the shadow, that is the projected point. Remember, yeah, projected point. And then with alpha, with 40 degrees, 50 degrees, whatever, we rotated this anti-clockwise such that u dash is now coming into xz plane. Now you remember whenever I rotated this u dash along with you know, with xz plane along anti-clockwise way. So whenever I brought this u dash onto z axis, this uz is now your d. So this entire d, whenever you start rotating, and ultimately you will now at some point of time you will come to z-axis. So this uz, the entire, no, I'm not talking about c. This entire uz is now d, and then you'll again come back to except plane, which we want essentially. So yeah, this is what we want. So u ultimately came to do double dash onto except plane. Now what is this point? This is that uz is your d. And since you are now rotating around y-axis, the y parameter is 0 and x parameter remains as such, that is a. And I told you already, once you start rotating u dash anti-clockwise, at some point of time, u dash will now become uz. That is, this d will now fall to uz. So this is b. Ultimately, this becomes a comma 0 comma d. That is, you are rotating via y-axis now. So the y parameter is 0 because it doesn't affect y-axis. X remains a as such, but the z parameter is now your uz, that is your d. Well, because I rotated at some point of time, u dash will now come to uz. U dash is this. Alright. So 2a's result is something like this. Now let us look for 2b. 2b, you should now rotate this u dash. Oh yeah, u double dash a comma 0 comma d, that is the output of the 2a. You rotate it anti-clockwise such that u dash will now align to z-axis. You can see here, rotate vector u after, that is u double dash is what? Vector u after rotation of xz, that is step 2a, about y-axis. Positive rotation angle, that is you are doing anti-clockwise such that u double dash will now align to vector uz. You can see the theory here. The z component is d, the magnitude of u dash, because vector u dash has been rotated onto z axis. Y component is 0 because we are rotating around y axis. It now lies in the xz. And now, yeah, you can also see the dot product in the cross products of vectors. I didn't use that here. I used the number to number. All right. So we'll now look at 2b. Now 2b, that is 2a's output is this a comma 0 comma d. Now if you look at this object, it falls here, and I need to rotate it anti-clockwise via some beta angle. So let me draw a normal 90 degrees perpendicular line. Now a comma 0 comma d means this is that a distance. 0 is of course y-axis, and d is this. That is what I told you here. So when you eventually rotate u dash to bring to xz, at some point of time u dash will now coincide to uz. So this d will now come to uz such that it looks something like this. So this is that d I'm talking about. So yeah, now this is opposite. This is the adjacent cos beta. Now you can see here cos beta adjacent by hypotenuse. So adjacent is d, which is equal to square root of b square plus c square. Adjacent is divided by. So what is hypotenuse? This is a, and this is, so square root of this square plus this whole square. So square root and whole square cancels, so it becomes b square plus c square. So it is essentially d divided by root of a square plus b square plus c square. Now, since we are dealing with unit vectors, so sum of that is the magnitude remains 1. It can be 1. So that is d by 1. It is d. Sine beta, opposite by hypotenuse. Opposite is a. Hypotenuse is this. So unit vectors a by this magnitude remains 1. So it is a by 1 is a. Now, what we did, what do you mean by this beta? To understand this, what do you mean by this alpha? I told you this is 90-degree. Okay, this alpha is rotation angle with respect to x-axis. Now let us say this is 50 degrees. Now what happened? You should keep on rotating this u dash 50 degrees. At some point of time, it will now touch uz. That is your d, and eventually keep rotating 50 degrees again, such that it is now at x-z plane, which looks like this. Now, to be what he says, you should apply this cos beta sine beta into the y-axis rotation, because you are now rotating. Step 2b means 2a means x-axis, 2b means y-axis. That is why this is 0. Now this beta, now let us understand this as 60 degrees. So what is the meaning? This u anti-clockwise, go here, keep on rotating 60 degrees, 60 degrees, 60 degrees, such that it now coincides with z-axis. So this entire part, not user, this entire part is now your coincided. Now we got cos beta, sin beta, dA from this. So substitute in y-axis. Why? Because step 2b talks about y-axis. Now y-axis matrix is this, and substitute wherever you have cos beta, sin beta. So we got this. This is equation. What is common sense? Common sense is something like this. This u has been now rotated to z-axis. One more common sense. We had this initial position. Step 1, we got this. P1 now came to origin. There is minus tx minus ty minus tz. Step 2, that is after doing 2a, 2b, you can see the arrow mark of P2. P2 is now here. P1. Why we did all this? You can see 2b ry of beta. Why we did? Because of we are done with T, step 1, step 2a, and step 2b. So one step, second step is done, 2a, 2b. Next step is rotating with theta. That is simple. Step 2a over. Now rotate that object with z-axis. That is pretty much straightforward. Perform the specified rotation about that coordinate axis called as z-axis, rz of theta, which is pretty straightforward. Z-axis equation comes, the z-axis matrix we know, theta cos theta minus sin theta sin cos. Z-axis remains unaffected, that is the reason it is 1. And theta he will give, we should rotate the object with 30 degrees, 40 degrees. Anti-clockwise means take it as positive, clockwise means take it as negative. So rotate. First step is over. Fourth step, apply, that is inverse rotation and inverse translation. These two are very, now before this, step 1 is done, T, Rx of alpha, Ry of beta is done, 2a, 2b, Rz of theta is done, that is the previous step. This is the one, Rz of theta. Now the last steps, that is inverse rotation, inverse translation. That is Ry of minus beta, Rx of minus alpha, and T minus. So whatever you have got all these equations, just inverse it. So you can see. So inverse translation, inverse rotation, the arrow mark went to the origin, and inverse translation. Push back wherever it was. If you have subtracted 10 10 comma 20 comma, remember step 1 we assume that it is, let us say P1 is at 10 comma 20 comma 5. In step 1 we subtract minus 10 minus 20 comma minus 5. In step 5 you add it 10 comma 20 comma 5. So whatever money you have taken here, you give it back. All right. So these are the theory and the mathematics. Conclusion is there is this u vector, and first step is you need to translate it translate it to the origin. Second step is rotate it with some alpha, that is 2a, that is rotating with respect to x-axis. Next step 2b, rotate that flow with some angle such that the axis now comes and coincides with the z-axis beta. The third step is rotate via z-axis with some theta angle. Fourth step, go back, that is this arrow mark should now come to rotate this arbitrary axis towards the origin, that is your inverse rotation, and next is inverse translation. So some 7 series of operations with some 5 steps. Now if we go back to that big deal equation, remember, just before going back, just a quick conclusion, quick summary. So step 1, now let us say this is the arbitrary axis, this red color, this dotted line is your vector, this this red color line is your unit vector, P1, P2, X1, Y1, Z1, X2, Y2, Z2. Bring this X1, Y1, Z1 to origin. So minus X1, minus 10, minus. If this is 10, 20, 5, minus 10, minus 20, minus 5. Will bring you this into origin. Step 2, yeah. This is ABC, you are viewing here, that means you are rotating via x-axis 0 BC, 0 Y, because it doesn't affect x-axis because you are rotating via x-axis. BC, draw the this is your view volume, and now draw a perpendicular line. Remember we did all this. And then cosine of alpha is C by D, sine alpha is D by D. Substitute it, we got this. So this is the projected point, this is the rotated. So step 2b, rotate that fellow with y-axis. Rotate it. So this is the rotated, and this is the perpendicular normal 90-degree beta opposite adjustment hypotenuse. So this got L square plus B square plus U square. And he has not, if you imagine that unit vector, if you imagine that vector, the entire cube as unit vector, you can take it as 1. Else you can just substitute as such. D by L. L we took it as 1. That is the reason we got this D here. This guy has taken as, has not equated to 1. So formula remains D minus A, AD. Step 3, rotate with z-axis, the z-axis equation with some theta. Step 4 and 5, inverse it. So finally we got this. Now we'll go back to that big deal stuff. Yeah, rotation about an arbitrary axis, not at all parallel to the coordinate axis. It was a big deal, right? Now we have understood why it's a big deal. You can see, bring to origin, 2A to B happens, now rotated. First, second is coincide 2A to B, third one rotated, fourth one go back, fifth one go back to 0. Now all these we have understood: matrix theory, mathematics, equation, some beautiful examples, beautiful video, all this. Now, as I always used to say, mathematics cannot be understood just by theory. You need to put it into practice. That means solve an example. Let's see that in a bit. Now take a unit cube which is having the coordinate axis something like this. What he says, find the new coordinates of the unit cube which has to be rotated 90 degree about an axis, that is that axis, defined by its endpoints 210 and 331. Okay, now what do you mean by this? Now this is the cube defined by its endpoints 210, 331 means that is your arbitrary axis. Arbitrary axis is 21, that is you can draw a line somewhere here. P1 is 210, P2 is 331. Now tell me, first step, P1 is 210, right? So you need to take 2 rupees, take 1 rupee, take 0 rupee, subtract it, such that 210 will now come to 000. Similarly, you should take 2 rupees from this 3, but because x-axis you have already taken 2 rupees here. So subtract 3 with 2. Y-axis take out 1 rupee, so it becomes 3, 3 minus 1, 2. And in 1 you should subtract 0 rupees, such that it comes something like this. You can see here 210. I need to subtract minus 2 minus 1 minus 0, minus 2 minus 1 minus 0. So that is P1 when it was 210. When you subtract minus 2 minus 1 minus 0, it will now come to 0, 0, 0. What about B? B, it was 331. Subtract 210, it will now become 121. Subtract 2 from 3, it is 1. Subtract 1 from 3, it is 2. Subtract 0 from 1, it is 1. So this is first step. That is bringing the axis to the origin, especially bringing the P1 to the origin. If you bring P1, obviously P2 follows. So this is step 1. Step 2 is what? That is 2a. You see here the projected point is somewhere here. You see 1 to 1. The projected point is now 0 to 0, 2, because you are rotating via x-axis, so it doesn't differ. That alpha we need to calculate. Now we got sine alpha. I think it is b by d, cos alpha c by d. So the normal, that is this step you will apply next step. I mean in the 2b, that is a square plus b square plus c square. So root 6 doesn't play here. So in the Rx of alpha equation, substitute your cos theta, so minus sine theta, sine theta, cos theta. This root 6 comes next slide. So this is your Rx. Ry, now you should rotate this guy with respect to y-axis. Rotate axis a dash b dash about the y-axis with some beta angle such that it coincides with that axis. Now this we know the formula. Sine beta is what? D by 1 in our case. Where in which case if we can consider that as unit vector. If we don't, it is sine beta is d, that is 1 divided by root of a square plus b square plus c square. So 1 square plus 0 square plus root 5 square, that is 1 square plus 2 square plus this is ABC. 1 square plus 2 square plus 1 square is your root 6. So 1 by root 6 when you simplify it will now look like root 6 by 6. So what you do is 6 can be written as root 6 into root 6. So numerator root 6 and denominator root 6 gets cancelled. It will now remain with 1 by root 6. So this is only for simplification purposes we have done that. So cos beta, you think it is A by D. So A is root 5. I mean, it is, yeah, cos beta is D. D is root 5 divided by A square plus B square plus C square is this one, root 6. So root 5 by root 6 can be written as root 30 by 6. Yeah, 6 can be written as root 6 into root 6. Root 30 can be written as mm, and yeah, you numerator by denominator, root 6 gets cancelled, and this is how it looks, root 30 by 6. So in substituting the ry beta, you will get this. And next step, rotate with 90 degrees, because the formula, the question says rotate that cube by 90 degree, and he has not specified clockwise or anti-clockwise. You can take it as anti-clockwise. So in the z-axis, this is 1, this is cos 90, that is 0, cos theta minus 90, minus sine of 90, sine 90 is 1, minus 1, sine 90 is 0. So this is the z-axis formula. Similarly, now you do the inverse translation, inverse rotation. Now these are those guys. This is the rotation, come from the beginning here, I mean from the right hand side. This is t sine of, that is 2a sine of alpha cos of beta. This is r z of theta. Now you go back. It is whatever money you have taken, you do it back. Inverse rotation and inverse translation. Inverse translation, you can see here, minus 2 minus 1 minus 2 minus 1 0 now becomes 2 1 0. Ultimately, if you multiply these 7 guys, you will get this equation. Remember, this is just r of theta. What is the original transformation, rotation transformation matrix? The new point is equal to r of theta. That is the entire thing into every point p of x comma y comma z. So you need to multiply these with x comma y comma z. That is x comma y comma z means these guys. So how many guys? 8 guys. 8 into the 24. So the ultimate, this theta should be multiplied with 8 guys. I will tell you how you should understand this. Okay. It is to be understood in the column wise. So 0, 1, 1, that is the first point. 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 1. The fourth wise remains homogeneous. Coordinate 1, 1. Multiply r of theta, whatever you got, all these values, with all the points, you will get this. Now, what is understanding? Now look column by column. The first point, now what is understanding? Once you rotate this particular cube by 90 degrees anti-clockwise, what's the question basically? Find the new coordinates by rotating this guy, which is at like 0, 0, 1, or 0, 1, 0, 0, 1, 0, 1, 1, 1, 1, 0, which is at this position. If you rotate the entire cube by 90 degrees clockwise, I mean anti-clockwise, by keeping that arbitrary axis 210331, which is parallel to any of the axes, ultimately it looks like this. Now, 0, 1, 1, which is 0, 1, 1, 0, 1, yeah, here, this guy. 0, 1, 1, if you rotate 90 degrees anti-clockwise, the new coordinate will be 2.6 minus 0.5, I mean 0.558 and 1.467. 0, 1, 0, that is the second column. 0, 1, 0, is this guy. This guy when gets 90, this guy when gets rotated 90 degrees anti-clockwise, he will now he will now position himself at 1.66, minus 0.484 and 1.30. Like this apply for all the points. So this is how the new coordinates. I believe we have now understood thoroughly how exactly you can rotate an object about an arbitrary axis which is not at all parallel to the coordinate axis. So this completes the rotation, 3D rotation. Three types. One is coordinate axis, second is parallel to the coordinate axis, third is not parallel to the coordinate axis. All these hangama we did for not parallel to the axis, coordinate axis. This completes truly the 3D rotation. Next, the pretty much straightforward ways like translation, that is scaling and sharing, reflection. So quick look at scaling. These are the 3D scaling parameter, uniform scaling, non-uniform scaling, same copy paste of your 2D. You can about any fixed point, about your view parallel to the coordinate axis. So just multiply, translate, scale it, and go back to wherever you are. So if you multiply all this, you'll get this equation. So this is the ultimate scaling equation for any fixed point. Next one is composite. That is, you can mix and match the reflection in the mirror object. This is the equation. Sharing, that is, pull the other faces of an object. So this is how the equation looks like. These are all pretty much straightforward. This is for unit vectors. Anyway, so that completes what is called as 3D transformations. I told you before, translation, scaling, sharing, reflection. These are straightforward. Rotation is perhaps a bit difficult. So we understood clearly now. And thanks for watching this. Any doubts, please put it in the comment section. I'll address it first. Thank you very much.